Hello everyone, today we're going to talk about kinematics and the SUVAT equations. First let's start with the notation and the formulas. So the notation of SUVAT. What is SUVAT? This notation is a simple notation to help you remember and focus on the formula that you need for kinematics. So we can start with S in the word SUVAT. S is the displacement, so not the distance, but the displacement, and we're going to talk about it maybe later in the next video. Then we have U, that is the initial velocity. That, of course, since it's a velocity, is the change in displacement divided by the time. Its unit, of course, is meters over second. And then we have the V as final velocity. Really important to remember that U is the initial and V in the final for the formulas. And V as for the U for the initial velocity, the final velocity is calculated with the change in displacement divided by T. And since it's a velocity, the unit is meter over second. Then we have A, that of course is acceleration. Acceleration can be measured by the change in the velocity, so final velocity minus initial velocity divided by the time, and the unit is meter over second squared. Then we have T, the time, and that the unit is seconds. Let's start with some formulas. These are the three basic formulas that then can give you, as you can see, other three formulas that are really important. So let's start for the first one. The first one says that acceleration, as we said before, equals to the change in velocity divided by t. And this brings us to be able to calculate for example, the final velocity being equal to the initial velocity plus at, or for example, the initial velocity being the final velocity minus at. Then the second formula, the most used, is that displacement equals half of the acceleration times time squared plus ut, so the initial velocity times t. This implies that with like some math in it, you can actually see that displacement is also equal to the sum of the two velocities times the time divided by 2. These are two really important formulas, and the second one especially because you don't have to know the time. You don't have to know, the acceleration, but you have to know the final velocity. The first one, you don't have to know the final velocity. So the second formula is especially useful if, for example, you have a problem and the final velocity is 0. So for example, a car that is stopping, you can just see that the final velocity is 0. So you can just need to know the initial velocity and time. Then the third equation, that for the third formula, is the final velocity squared equals to initial velocity squared plus 2as. This implies, of course, that the displacement equals v squared minus u squared divided by 2a. And if you want to calculate the acceleration, it's basically the same. Acceleration equals v squared minus u squared divided by 2s. Let's go now onto some graphs. Okay, so this first graph we're going to talk about is this displacement versus time graph. Displacement is in meters in the y-axis. The time is in seconds in the x-axis. We can focus mainly with the red line. So the red line has three phases, A, B, and C. In phases A and C, we have a steady speed, and phase A is a positive speed, C is a negative speed, and then B is stationary, so it's not moving, the speed is 0. How can we calculate these speeds? It's pretty easy. Watching the graph, for example, let's focus on the A. So the object is moving from 0 to 8 meters. So the displacement is 8 meters, 8 minus 0. And the time, it takes 4 seconds to do those 8 meters. So by the definition of velocity, that is the change displacement divided by the time it takes, it's 8 minus 0 divided by 4. So 8 divided by 4, that is 2 meters per second, 2 meters divided by second. Then we have the second velocity, VB. As we said, it's stationary. We can see because it's not moving, it's not changing his position. But we can actually calculate this also in a mathematical way. We can say that since it's the change in displacement, we have the final position is 8 meters. The initial position is 8 meters, so 8 minus 8 is equals to 0. Then it is divided by 3 seconds, so still it's 0. The speed is 0. Then we have the third phase C, with the velocity 3 or velocity c. It's a steady speed and it is returning to start. So what happens here is that the displacement, the change is what is the final displacement? The final distance is 0. The final position is 0. 0 minus 8 because it's the initial position, so it gives negative 8 divided by 3 because it is the time it takes to get from that point to point A meters to point 0 meters. And this gives us a negative velocity of minus or negative 2.67. Then we have the second graph. Second graph is about velocity versus time. Velocity in meters divided by second in the y-axis and time in seconds in the x-axis. We can focus again on the red line. So this graph is a little bit more tricky because in the first part, we can see it's a constant acceleration because it is improving the velocity. The velocity is changing and it's going to be greater each second. Then we have like a moment where the velocity is constant velocity at 8 meters divided by seconds. And then it's a constant deceleration that is actually acceleration, negative acceleration that makes the velocity return to 0. How can we calculate the acceleration first? The acceleration, by definition, is the change in velocity divided by time. So for the first part, we can say 8 minus 0, so the change in velocity divided by 4, the time, is equals to 2 meters divided by second squared. Then A2, so for the second part, it says constant velocity, so change in velocity is 0, divided by 3, the time it takes, so it's at 0 meters divided by second squared acceleration. The velocity is not changing. Then we have the third one that we expect to be negative, and it is the same as the graph before. So we say that the final velocity is 0 minus 8, the initial velocity, divided by 3, the time it takes, so negative 2.67 meters divided by second squared. Now this is a pretty cool feature of, let's say, of this graph, velocity divided by time, that we can calculate the displacement in each portion of the graph, just calculating the area that is below the line. For example, in the first part, so in the constant acceleration between time 0 and 4, if we want to calculate that displacement in those 4 seconds, we can just calculate the area below the red line. This area now, for example, in this, the first phase is a triangle. So we can say the base times height divided by 2 is the displacement. The base is 4 seconds, the height is 8 as the velocity, and then we have divided by 2. So 4 times 8 divided by 2 equals 16 meters. That's the displacement of the first part. Then for the second part, we can see it's a rectangle. So it's just base times height. So it's 3 times 8, 24 meters. Then we have the third part, there's still a triangle, and it's 8 times 3, base times height, divided by 2, so 12. If you want to calculate the total displacement, the total distance traveled, we can actually just sum all the 3 components, or we can actually just calculate the area below all the red line. The area below all the red line is in this case, is a trapezoid. And to calculate the area is the sum of the bases times height divided by 2. So I have 10, the time, the major basis, the greater base, plus 3, the smallest base, time the height, so 8 divided by 2, so 52 meters. It's actually 16 plus 24 plus 12. The third graph is acceleration versus time. This is the simplest graph where the acceleration is constant. And yeah, the acceleration is constant, as you can see in this graph. This means that still in the graph velocity versus time, the velocity is getting greater and greater. The change in velocity equals at. This means that, of course, what we said before, a equals the change in velocity divided by t. If u is 0, this implies that v equals at. So that means that, as for before, if we can calculate the area, like if we say that in the graph the time goes like the acceleration is, for example, 5 meters over second squared in a time of 10 seconds, so 5 the acceleration in 10 seconds, we can calculate the change in velocity getting the area of that rectangle, so a times t, so 5 times 10 in that particular occasion, so 50 meters over second. That's the change in velocity. But if u equals 0, the change in velocity equals the final velocity. Let's do some exercises. So the first exercise says a car is at rest at a parking spot. The driver then decides to pull away and go to the supermarket. After 5 seconds, the car reaches the speed of 36 kilometers per hour. What was the acceleration of the car? So first of all, we have to write the datas. Here it seems we just have two datas and they are not enough, but the text usually gives you a third data, that is in the start of this first sentence, a car is at rest. It means that the initial velocity is 0. Initial velocity is 0, the final velocity is 36 kilometers per hour, and the time is 5 seconds. Now, the final velocity, all the velocities, we want to have them in meter over second, not kilometer over second. So 1 kilometer of 36 kilometer over seconds is equals to 10 meters over second. So if you have a velocity in kilometers over hour, you just have to divide by 3.6. And then we want to find acceleration, so this is pretty easy. It's like the definition of acceleration, the change in velocity divided by time. So we have 10 minus 0 divided by 5. The time equals to 2 meters over second squared. Next exercise says a plane is rolling off from rest from the runway. Its acceleration is 10 meters over second squared, and after some time t covers a distance of 80 meters. Find t. So here we have, as before, the acceleration, 10 meters over second squared. Then we have the displacement, 80 meters. And then we have the initial velocity being 0. And we want to find the time. How is this possible? How can we find the time? So we can use the formula. There are many formulas, but we can use the formula S equals half a times t squared plus ut. This gives us that t squared, because u is 0, t squared equals to 2s divided by a, so t equals to the square root of 2s divided by a. This gives us 2 times 80 divided by 10, so square root of 16. Be careful now, the square root of 16 is not just 4, it's plus or minus 4. This means that we have to choose between plus or minus. Since it's a time, we're going to choose plus because we're not interested in what happened before, because time is not negative. So we're just going to keep the plus, so time equals 4s. Final exercise is a rifle is fired at the wall. In traveling the 70 centimeters along a rifle barrel, the bullet uniformly accelerates from rest to a velocity of 210 meters per second. Find the acceleration involved at the time taken for which the bullet is in the barrel. So here we have some data. First of all is the length. So the displacement is 70 centimeters. 70 centimeters is 0.07 meters. The bullet uniformly accelerates. It means that it has the same acceleration. Then from rest, so initial velocity is 0 and final velocity is 210. And we need to find the time and the acceleration. Here we can use a formula that I explained before in the presentation, as equals v squared minus u squared divided by 2a. So we can calculate the a, since it's the only number that we don't know in this formula. A equals to 210 squared minus 0 squared divided by 2 times 0.07. This gives an acceleration of 315,000 meters over a second squared. Be careful also, just try to, when doing physics, when doing this type of exercise, just try to understand, is this a, this number, does this number make sense? That's the most useful thing in physics. It's a big acceleration. So if it was for a car, it wouldn't make sense. But since it's for a bullet, it makes a lot of sense. So this result seems fine. Then to calculate the time, we can use another one. So time equals v minus u divided by a. So time is 210 minus 0 divided by the acceleration, and s equals to 0.00067 seconds. Also here, the time is really small. Doesn't make sense. It does. The velocity is really high, the acceleration is really high, and it's a bullet. That's all for this video. We're gonna see you guys again for the projectile motion in the next video. Thank you.